I think I might have lost those derivations that we did, but I have another link. I think they're actually on the website. Let me take a double quick look. I just closed the thing. Oh no, they're in your homework, aren't they? The derivations, are they in your homework? Is that true? No, they aren't. Alright. I'll look and see. I think I might have made some videos for those derivations if y'all need to review them or whatever, but if I can find them, I'll send them out to you. But you can also find them online as well. But if y'all have questions about them, I'm sorry, I didn't mean to close that, but I'm pretty sure I have that. Let me write a note to myself. Mark it for a second. All right. So we want to find the total moment of inertia. So we're going to treat this as two separate objects that are coming together. We'll do this in a little bit later in a problem where we have an axle that's rotating and it engages with another axle, and so it makes for a little more practical scenario. But here, if we think of Richard Pryor on the Wonder Wheel, we can treat it as a hoop, or like a hoop that we did before, where the moment of inertia is just mr squared. And then we can also treat them as a cylinder, where Richard Pryor is the cylinder, because we're basically cylindrical if you think about it, right? A cylinder, sort of. So we're going to treat him as a cylinder. Is he going to rotate about this axis, or is he going to rotate about this axis? The second one, right? Yeah. So because he's rotating around. Actually, more particularly, he's rotating about this axis. But if you're really a cylinder, it doesn't matter if this is the same, right? Because you're symmetrical. So we can just treat it as a hoop and a cylinder. The hoop has a moment of inertia of mr squared. That's in this table up here that we've already defined it. And this is for the Wonder Wheel. Let's see, I made some assumptions about the mass. I'm just going to use what I have. I said that it was about 10 kilograms, the mass, and then the radius of that Wonder Wheel is about what, you think? It's about 2 meters across, right? The diameter, because Richard Pryor is about 2 meters tall. He's pretty tall, so it's about 2 meters across. So that gives a radius of the Wonder Wheel about half that, or about 1 meter. So the radius of the Wonder Wheel is 1 meter, and then that's squared. So that gives us a moment of inertia just of the wheel of 10 kilogram meters squared. And then for the cylinder, it's a little more complicated because we have to take this into consideration. So it's going to be a quarter mr squared plus a 12th mv squared. And this is the mass, radius, and height of Richard Pryor. So the mass of Richard Pryor, let's see, I don't know if I used 100 kilograms as his mass. That might be a bit of an overestimate, but just, he's kind of a big guy. He's pretty tall. And a radius, that's going to be r. This is the distance from here to here, which is approximately how far? This distance. Like a 1/2 quarter to a 1/2 meter, right? So I said between there was about 30 centimeters, or 0.3 meters. And then his height, we've already said, this is our B term, which is the length of the cylinder, is 2 meters. So he's about 6 foot tall, a little more. All right, so if I do a quarter of 100 times 0.3 squared plus a 12th of 100 plus 2 squared times 2 squared, that gives me a moment of inertia of 36. all right, which gives us a total moment of inertia for the whole system of 10 plus 36 kilogram meter squared, or 46 kilogram meter squared. The point there being that if you have two objects that come together, their moments of inertia just add up. Which shouldn't be a big surprise, because moment of inertia is just the sum of mr squared. And so if I add more mr squared, I just add them all up together. It's just a summation. Alrighty? You with me on this? Do this? Okay. Let's have a quicker question next. You have 4 balls, each with a mass of 1 kilogram. They're attached with rigid massless rods on the corner of a square. Each rod is 1 meter in length. What is the moment of inertia? They're rotated on an axis that cuts the middle of the square, and then this thing is rotating like this. What is the moment of inertia? These are just discrete particles, so you won't need your table. You'll just calculate the moment of inertia, assuming these discrete particles. All right, let's stop in about 5 seconds. Just guess if you don't know. Stop at 2:12. That's everybody. Okay, very good. I just do the sum of mr squared. That is, each of these is 1 kilogram. Each is a meter apart from the squares. That means that this distance is a half a meter. So it's just going to be 1 kilogram times 1/2 meter squared. But then I sum it up for all 4 particles. But since all 4 particles are the same, I'll just multiply by 4. That's 4 times 1/4, or 1 kilogram meter squared. So D is the right answer. So what I mark? Yeah, good job. All right. What did the dog say after a long, hard day? Rough. Okay. Good job. Let's see. All right, so we're gonna get a new second law. First, let me tell you though, on Friday, I'm not gonna be here, so we're not gonna have class at all. I'll send an email out to the class. I'm going on a field trip up at St. Francisville with my son, so we're gonna have plenty of time. We're gonna wrap up this chapter, maybe even on Wednesday, and then next week we'll spend we might have a little bit left on Monday of this chapter, but most of next week will be spent on elasticity and equilibrium, which I said will be a take-home portion of your exam, and that portion won't be due until after the Thanksgiving break, so you'll have all break plus a couple of days to work on that. All right, so no class on Friday. I'm sorry if that's inconvenient for you. That's just the way it is. So. You can take it up front, get my pay docs or whatever. All right, so Newton's second law. When we were dealing with linear motion, Newton's second law was F equals ma, right? But this also applies when we have objects that are rotating. And so we can sort of do this idea where we've been separate or replacing linear variables with rotational variables. Let me just remind you what we have so far. We have theta, or excuse me, x, we replace with theta. So whereas before we were talking about linear motion, when we talk about rotational motion, we talk about the angle theta. For v, now we have omega. For a, now we have alpha. For force, now we have torque. We sort of call that like an angular force. It's a force at a certain moment arm. And whereas before we had mass, what do we have now? What's the variable that we use? You're right, the moment of inertia, I. So mass was a measure of inertia. I is a measure of the moment of inertia. So these are our linear quantities on the left and our rotational quantities on the right. So since I is a measure of the moment of inertia, or the rotational inertia, and alpha is the rotational acceleration or the angular acceleration, we can rewrite Newton's second law. Instead of F equals ma, we'll say what? What's our analog for F? Torque. We'll say instead torque is equal to not m, but I, and not a, but alpha. These are all vector quantities except for I. So this is going to be Newton's second law restated, but for a rotational frame. And everything that we did with Newton's second law will apply here as well. I'll show you several examples, and you have several in your homework as well. Also, as before, torques in the clockwise direction are considered negative, and those in the counterclockwise direction are considered positive. Right. But if it's going in the clockwise direction, that doesn't mean that the direction of the torque is clockwise. Remember, the direction of the torque comes about from the cross product. It's actually going to be perpendicular to the rotation, orthogonal to the rotation. All right, so if it's rotating in this direction, our torque is actually in this direction. All right. All right, let's do an example. At first, this might seem like a lot of steps, but once you get the hang of it, it's pretty easy. Let's say that I have an object here. It's a disk. It has a radius of 1 meter, and there are a couple of forces acting on it. I want to know what is the moment of inertia. I didn't write it here, but I'd intended the mass of this disk is 1 kilogram. All right. Several steps here I want to take. The first step is I want to find the moment of inertia. This is a cylinder. A disk is just a flat cylinder. So that moment of inertia from your derivation, or from that table, which will be on your equation sheet, is 1/2 mr squared. So I can calculate that. That's 1/2 of 1 kilogram times 1 meter, which is the radius, squared. So it has a moment of inertia of 1/2 kilogram meter squared. The next thing you want to do is you want to find the torque, the net torque. I have torque 2 here and torque 1 here. I want to find out which of those is positive and which one is negative. Is torque 2 positive or negative?
That's negative.
This one is negative because it causes it to go clockwise. Torque 1 is positive or negative?
Positive.
Positive, right. So if I imagine a force pulling up in this direction, it causes it to rotate in the counterclockwise direction. So torque 1 is positive and torque 2 is negative. So I have a positive torque 1 and a negative torque 2. So my net torque will be torque 1 minus torque 2. which is going to be 1 Newton times the length of the moment arm, which is 1 meter, minus 2 newtons times 1 meter. So my net torque then is 1 minus 2, or negative 1 Newton meters. And then the next step is to apply Newton's second law. The sum of the torques, or the net torque, is equal to I times alpha. Right, so this is negative 1 Newton meter equals to 1/2 kilogram meter squared times alpha. So that means that alpha equals negative 2 radians per second squared. Because it's negative, that means that it's in the clockwise direction. Next time I'll show you some problems like you might see in your test. This is a pretty simple problem, but I'll show you some that are slightly more complicated. You can include the cross products in here and find the net torque using your cross products. But they all sort of follow these same steps: finding your moment of inertia, finding your net torque, and then applying Newton's second law. You can also throw in some kinematics. So, for example, if I ask what is the angular speed after a certain amount of time, then you would say, well, the angular speed is omega naught plus alpha t. And then once you find that angular acceleration, you can find the angular velocity. We have about 7 minutes. I'm going to do, or about 5 minutes, do just a few clicker questions while they're all sort of fresh on your mind. All right, so here we have 2 spheres. They have the same radius and equal masses. One is made of solid aluminum, and the other is made of a hollow shell of gold. Which one has the bigger moment of inertia about an axis through its center? So 2 spheres, they have the same mass and same radius, but because one is made out of gold, which is a lot more dense, all of its mass is located at the outer radius. So which one has the bigger moment of inertia? The aluminum, the gold, or are they the same? About 10 more seconds. I'll stop at 1:15. I think that's everybody. 3, 6, 9, 11. Yeah, that's everybody. All right, let's see. All right, it is the hollow gold. In fact, if you look back at our at those equations on your little table for moments of inertia, for a solid sphere, the moment of inertia is 2/5 mr squared. That's for the solid sphere. And for a hollow sphere, it's 2/3 mr squared. This is our hollow sphere. And of course, 2/3 is bigger than 2/5. So the hollow sphere, because it has mass all at large radii, will have a much larger moment of inertia. It has the bigger moment of inertia because all of its mass is located out at r, equal at a large r. And since r is squared in moment of inertia, that carries a lot of weight with the moment of inertia, a much larger moment of inertia. Oh shoot, let's see, give me just a second. We'll come back to those other questions. Let's skip ahead a little bit. 4 T's are made from 2 identical rods of equal mass and length. Rank in order from largest to smallest the moments of inertia. So ranking them from largest moment of inertia, this is A, B, C, and D. Which one has the largest moment of inertia, the next largest, and the last largest? You're looking, the one with the largest moment of inertia will have the most mass out at large radii. And the one that has the least moment of inertia will have the least mass at small radii. Well, I mean, will have the most mass at small radii. Notice A and C are both listed in all those options. Which of those has the largest moment of inertia, A or C? A does, right, because it has all this mass out at large radii, but C, most of the mass, half of the mass anyway, is at R equals 0. So A will have a much larger moment of inertia than C will. I'm sorry, let me start that. We'll make this the last one. So what's after A? All right. Stop at 35. I think y'all answer faster when we're about to get out. Is that true? Oh, D is right. Good. D is the right answer. Just give me 20 seconds. So A, we've already said, has the largest moment of inertia. D is next because it doesn't have any mass on axis, all right, in comparison to B, which has, or excuse me, yeah, B, which has a lot of mass on axis. But this one is a bigger moment of inertia than this one because it has mass out at this large radii, whereas this one only has mass out to half the radius because it splits that one rod. All right, we'll do this a little bit more. I think there are a couple more questions regarding this on Wednesday, and no class on Friday, and those derivations for the exam. Take home. You'll bring it in on the day of the exam. All right. Y'all have a good day. Sorry about losing that video.